Okay, welcome everybody to this Crypto Cafe talk. It is our pleasure to have somebody who has both academia and academic and industry experience with us today. And going to talk about zero knowledge proof, something that we're actively looking at, but from an industry perspective. So thank you very much, Xinxin, and the floor is yours.
Cool. Yeah, thanks for the introduction. I'm happy to give an overview about zero knowledge proof more from the industry perspective. So zero knowledge proof itself is a very complex topic. Instead of diving very particular protocols or systems, I would like to give you an overview how we view this topic from the industry and which research direction we can keep exploring through the collaboration between the industry and the universities. Okay. My name is Xinxin. I'm head of cryptography at IoTeX. Yeah, let's start with today's talk. I'm going to talk about three topics. The first one is a state-of-the-art overview about zero knowledge proof. Basically, give you a timeline regarding the innovations along these directions during the past few years. Second topic will be I'll be talking about some major use cases we are from the industry they really care about. Also, the third topic I would like to mention about some research opportunities. I think this will stimulate the collaboration between university and university and industry to tackle those challenges altogether. Okay, let's get started. Yeah, so the first problems, what are the zero knowledge proofs? Of course, from the cryptography, we have the very rigorous mathematical definition about a zero knowledge proof. Generally speaking, it's a type of method which allow a prover, one party, which is usually called a prover, which can prove to another party, also called a verifier, that a given statement is true while avoiding disclosure of additional information beyond this fact. Okay. This is a description in the cryptography textbook. Also, we have the corresponding mathematical definitions for this. From the industry perspective, the classical cave examples still serve the best explanation to show the developers and to show the communities how this concept really means through this interaction. Interaction. Okay. Yeah, we all know zero knowledge proof have three very important properties. First one is completeness, which means if a statement is true, the prover must be able to convince the verifier that the statement is true. Second property is soundness. Right? So if the statement is false, then the prover cannot cheat on the verifier, except with negligible probability. Third one is zero knowledge, which means verifier learns nothing beyond the statement of validity. So these three salient properties establish this direction and made zero knowledge proof a powerful tools can be used in a wide range of applications. Yeah, firstly, let's look at a bit of history about zero knowledge proof, right? So as a cryptographer, when we were at when I were at a university, working for my PhD, zero knowledge proof it's still a very important topic, but most of them are more theoretical interest, right? So the concept of zero knowledge proof can trace back to the mid-80s. The origin paper by Goldwasser, Micheli, and Rankov. They introduced this concept in 1985. So, and they provide some constructions to prove the quadratic residue or non-quadratic residue. In 1992, there is another very important work called sum check protocol. So this work proposed by Long et al. They introduced this subcheck protocol. Basically, we'll be able to reduce a claim over the sum of multivariate polynomials evaluation to a single evaluation at a random chosen point. Then in 2007, there's another interactive zero-knowledge proof protocol called GKR protocol. Right? So in this case, the GKR protocol, the prover can run linearly, and the verifier can run sublinearly in number of gates of the circuit. In 2010, there's another very important theoretical work called KZG, polynomial commitment. So this work, actually, they introduce a polynomial commitment scheme based on bilinear pairing. So the unique characteristic of this protocol is that the commitment only consists of a single group element. So all of those work in the early stage establishes a foundation for the later innovations. Many of these early stage protocols has been further explored during the past few years to make it can be used in the different industry applications. They have become the very important building blocks to create other zero-knowledge proof systems and protocols. So why a theoretical topic in the crypto community suddenly become hot in the industry? So I think the story come from the Ethereum. Right? So around 2018 until 2021, we see there's a few occasions there's a significant transaction fee surge on the Ethereum platform. Ethereum, if you don't know, it's one of the top blockchain platforms to host the decentralized applications. So why the transaction fee surges on the Ethereum? Because there's some popular applications and a lot of people will using that applications, which cause the network congestion. Under such situation, the transaction fee, if you want to post a block on the Ethereum, will increase significantly. So this is actually quite natural phenomenon if we consider a decentralized system like a blockchain. Basically the founder of Ethereum, Vitalik, described the scalability trilemma for blockchain systems. So essentially, you cannot achieve all of those three properties altogether for a blockchain platform, which including platforms is scalable, decentralized, and secure. The popular blockchain platforms like the Bitcoin or Ethereum, they choose the decentralization and the security, which means they sacrifice the scalability when they firstly design such system. They think this decentralization and security are most important properties for their platform. So this trilemma actually caused the transaction fee surge when we observed in the past years for Ethereum platform. So how to address this issue? Actually, Ethereum has a very ambitious roadmap to particularly address this issue, and the zero-knowledge proof has been chosen as one of the core technology to address this challenge. So basically, Ethereum will outsource all the executions to a layer 2 network, meaning you have another node which running off-chain to perform certain operations or computations on top of the transactions. After the computations has been done or has been processed, a zero-knowledge proof will be generated to validate the integrity of this process. So this is a high-level idea how zero-knowledge proof has been used in the blockchain domain. We will talk more details later about this particular scalability solution. Okay. Based on this, Ethereum established a rollup centric roadmap. It's a very complex roadmap. I only show the phase which are highly relevant for the zero-knowledge proof. So basically, zero-knowledge proof will become one of the core or fundamental technology which can be used to address the scalability challenge for Ethereum. So Ethereum will go through a number of iterations before integrating this technology to the full production manner. So by combining multiple pieces. So essentially, Ethereum will choose a certain data availability layer to store the transactions and use zero knowledge proof or what they call the ZK rollup to process the transactions or to batch the transactions and to generate a zero knowledge proof. This proof will be eventually validated on the Ethereum blockchain, and all transactions will be accessed. Will be accepted in batch in such scenario. Okay. So after Ethereum establishes the rollup centric roadmap, zero knowledge proof has become an extremely hot topic by the blockchain or Web3 community as well as the academic community. Actually, I would like to say it's become the golden years for zero knowledge proof from the more theoretical perspective until today. It's become more practical and can be really deployed in the practice to address a lot of industry applications. So the existing innovations in the zero-knowledge proof can be roughly classified into two categories. A lot of zero-knowledge proof systems they are using elliptic curves and bilinear pairings, right? So there's a lot of nice properties, especially for bilinear pairing. All the innovation actually starting from the 2013. Pano et al. They proposed the first nearly practical zero-knowledge proof protocols based on the quadratic arithmetic program or QAP. This is a first nearly practical zero-knowledge proof protocols. Later on in 2016, Gross proposed the well-known Gross 16 protocols. This one still very important, although they have been proposed many years ago. This Gross 16 has a very it's a efficient proof systems. They work on the statement which can be represented in a certain type of circuit. A unique property for Gross 16 protocol is that they have the smallest proof size with only 3 group elements. And also they have fast verification only involving 3 pairing computations. So Gross 16 protocols has been one of very popular protocols which has been deployed in multiple blockchain systems and applications. So the compact size of the proof is a very important feature for blockchain applications. So which enable blockchain applications can use smart contract to verify the proof in a decentralized manner. Later on in the same year, Bottle et al. They propose what they call the bullet proof. This one is based on the discrete logarithm problem, and they basically show how you can open the Patterson commitments, which based on the inner product arguments. So this is also very important zero-knowledge proof protocols because it does not require what we call the trusted setup. In 2019, actually, there's a number of proposals for about zero-knowledge proof. So this family of zero-knowledge proof, Sonic, Planck, and Martin, they all try to address very important issues in the zero-knowledge proof. Early stage proof systems, they all require trusted setup, which means you need a process to establish common reference string in a zero-knowledge proof systems in a trusted manner. So after the pre-processing or setup process, all of the secret should be securely removed before you can really using that system. Sonic, Planck, and Martin, they introduce what they call the universal or updatable structure reference strings. So in this way, they can address the problem of the trusted setup. So instead of conducting the trusted setup, each time when you try to generate a proof, you can actually generate a setup, conduct a setup process at the very beginning, and you can continue using those parameters. Yeah, that's a big advantage. Also, I think it's a big advancement for zero-knowledge proof. This represent the first categories of innovation before 2019. So people continue propose new proof systems which have less security assumptions. Also, definitely they need to make certain trade-offs. Okay, that's the previous innovations basically can allow you to generate a zero-knowledge proof in a practical way for certain statement. However, we are still facing the challenges when we're dealing with other applications. In 2018, 2020, there's a number of works about lookups. That's why lookups become relevant because there's functions which are definitely not zero-knowledge proof friendly. It become very hard to represent the operation of those functions in terms of the circuit. This lookup approach actually they allow you to prove that a value is included in a pre-computed table using what they call the grand product check. Yeah, so this way you can actually capture a complex function, for example, the hash function, like SHA family of hash function, using a lookup table. You don't need to represent them into a arithmetic circuit or other type of circuit anymore, and you can use a lookup table to prove certain values included in that table. So this lookup family of work has been further extended or improved to further reduce approval time and verifier time. There's many subsequent work has been working on this direction. Also, from 2019 to 2022, there's additional works which further extend the commitment scheme to multivariate polynomial case, try to capture more complex constraints when you're building the zero-knowledge proof circuit. Instead of early circuit, you may only deal with addition or multiplication gate, and in the later works you can deal with more complex circuit type. Besides those innovations, another very important family of works, what they call the folding schemes. So this category of works, they try to address the aggregation issues in the zero-knowledge proof. Essentially, how you can combine multiple zero-knowledge proof together in a more compact form and in an efficient way. the one of very important work called NOVA. It's basically a folding scheme try to achieve incrementally verifiable computation. So this this aggregation type of proof systems will be very useful when you're dealing with the system with streaming type of data. For example, your transactions in the blockchain systems keep coming into your system, and you try to generate a proof. Every time you receive a new transaction, or in a Internet of Things setting, your device or sensor keeps sending the data periodically, and you still want to consecutively generate proof to show what's happening in the physical world. So this folding scheme has also have a lot of subsequent work, try to improve the performance and improve the aggregation process. So this is also a very important family of works. So these two slides we show the practical zero proofs. They basically using the elliptic curve and the bilinear pairing to try to achieve the compactness of the proof, also to have the practical performance. Another line of very important works is to building zero-knowledge proof using hash functions. This line of work actually they start from the 2013. The first work is called the tiny RAM. The reason for building this type of work is to, instead of only prove a certain statement is true in a zero-knowledge manner, how can we prove a virtual machine has been execute the instruction correctly? So if we can address this challenge, actually we can compile a practical problem or the statement you would like to prove into a virtual machine instructions. Then basically we can prove a lot of different statement in a very simpler manner. So you only need to write your statement in the high-level programming language and running in certain type of virtual machine. So once you have this virtual machine instruction or operation code can be proved, you can actually to prove any type of statement which can compile into the virtual machine instructions. The first work starting at 2013, it's called Tiny RAM. It's Ben Salson et al. They actually developed a snark, based on the probability checkable proofs. So this system allows you to prove the correctness of execution of a C program. This program will be compiled to Tiny RAM. Tiny RAM actually is a predefined instruction set. So once you can prove all the instructions in the Tiny RAM virtual machine, you can actually prove any the C program compiled to the Tiny RAM instruction set. So this actually unlock a lot of applications in the real world, also facilitate the developers to use zero-knowledge proof technology. Very important work has been published in 2018 called the Starks. It's still from the Ben Salson and his co-authors. The Stark actually is built using the collision resistant hash functions as well as error correction code. They combine multiple technology together to build what we use today, the Stark proof systems. Starks does not require a trusted setup, and also they are very fast in terms of the proving and the verification time. Also are conjectured to be post-quantum secure. They are building from the hash functions. If of course if the hash functions if the post-quantum security is your primary concerns, all the elliptic curve based zero-knowledge proof definitely cannot be used anymore. but you need to go to the post-quantum zero-knowledge proof systems like Stark. So yeah, this is basically cover the many important work of the extensive period of innovations in the zero-knowledge proof directions. Yeah, of course, it's not it's not it's not complete. There's a continuous innovation even in this year in terms of how you can represent the circuit in the different way, how you can use other type of commitment schemes to build zero-knowledge proofs. Yeah, this one actually give you this table actually give you a comparison among the different zero-knowledge proof systems. This table is produced by the Crypto Media Capital. You can take a quick look. You can see there's a lot of trade-offs when you dealing with zero-knowledge proof systems in terms of the proof size, proof time, verification time, etc. Whether you need your system to be quantum resistant. So the different schemes has been target the different trade-offs when they design their system. Definitely you need to have your application in mind to see which factors is most important to you. We can see graph 16 they actually has very little proof size. Only three only three group elements, which make it very useful in the blockchain domain. Although they need to do the trust setup. Other zero-knowledge proof systems, some of them have very large proof size. Others has a relatively smaller size. Proof time, verification time is all vary a lot. Some schemes they require the trusted setup like graph 16. Others, Sonic, Planck, Martin, they don't need to do the trusted setup for every proof generation. Yeah, the Coinbase venture actually actually summarize the different projects which has or startups which has been working on the zero-knowledge proof domain based on all the innovations has been proposed by the academic communities. Yeah, we can see there's maybe tons of zero-knowledge proof focused projects. They have been working on the different topics during past years, like hardware acceleration, coprocessor, how to do the trustless transfer between the different blockchain systems. Also, how can you use this one to build a private blockchain, etc. So actually, billions of fundings have been poured into this domain, and maybe hundreds of startups working on the different topics in the zero-knowledge proof. Yeah, that's why we can see a very large landscape for the different startups which has been working on the different topics or different aspects of zero-knowledge proof. Yeah, based on the research, based on the marketing research, actually the zero-knowledge proof generation will become a 10 billion market by the year of 2030. So that's why we can see there's a lot of potential for applying this technology in the different industry domains. So if we only consider the Web3 or blockchain applications, this particular application will require almost 90 billion zero-knowledge proofs to be generated in 2030. So the blockchain or Web3 system applications still remain the big customers for this zero-knowledge proof technology. However, you can definitely extend this to traditional industry. Okay. Next I'm going to talk about some major use cases and help you to better understanding which particular problems industry has been focused on using zero-knowledge proof. Zero-knowledge proof actually will be used in two different patterns, two different categories. The first category definitely is to use zero-knowledge proof to address the scalability. Originally, these problems mainly remaining on the blockchain domain, but of course you can use a similar approach to address the scalability issues in your traditional Web2 based systems. Yeah, like I mentioned before, for blockchain like Ethereum, they have been facing the scalability issues or the gas fee surge issues for quite a while. One solution is to move the execution to what they call the layer 2 networks. Yeah, the idea is as follows, right? So we have we still use Ethereum as a blockchain platform, but only use their decentralization and security properties. All the transaction processing, instead of being processed sequentially on the layer 1 network by the smart contract, all the transactions can actually be outsourced to a layer 2 roll-up node. The idea I think is very interesting. Off-chain node actually you are going to collect all the transactions to be processed. You batch them together and perform the operations on those transactions. Those transactions will change the blockchain state from A to B after you apply every transactions. During this process, you also can generate a snark or stark proof, showing to the outside you are performing the transaction or state transaction correctly during this process. This proof will later be submitted to the layer 1 blockchain, for example, Ethereum. This proof will be validated by a smart contract in a decentralized manner. So in this way, you can leverage the security on the layer 1 blockchain together with zero-knowledge proof. Once the proof validation is succeed, all the transactions in this batch will be accepted and become finalized. So in this way, the Ethereum can effectively address the scalability issues, because you can open nodes, you can deploy a very powerful nodes to batch many transactions all together and use a compact proof to show the layer 1 blockchain all the transactions have been processed accordingly. So we can see zero-knowledge proof play a very important role, basically to attest the off-chain computation has been performed correctly. Yeah, this is a very large category of techniques, so-called the ZK rollup in the blockchain domain. So many startups has been working on this direction and to optimize the entire process. So this is how we use zero-knowledge proof to address the scalability challenge in the Web3 or blockchain domain. You can, like I mentioned, you can definitely using the similar techniques to the other more traditional Web2 based applications. Yeah, second category definitely is to apply the zero-knowledge proof for privacy. So like we know, the zero-knowledge proof has that zero-knowledge property, which bring the privacy advantage. So for scalability applications, like I discussed here, which does not need to hide anything, right? So the transaction will be is published on chain, and you only use zero-knowledge proof actually as a validity proof. For more privacy focused applications, definitely you need to use the zero knowledge property. So while in the blockchain domain, it's called the ZK rollup, but it's only actually just a validity proof, not using any privacy case here. Yeah, for privacy property, actually you can use the zero proof to build a more privacy focused blockchain to hide every transactions. Yeah, like the early stage, what they cache did, and many recent products, you can actually build the privacy layer on top of the blockchain using this privacy property. Other very important category application is in the identity domain, right? So zero knowledge proof actually enable an identity holder to prove he actually is the owner of a credential that meet the certain criteria without showing the actual credential. For example, if you have a digital driver license and yeah, you can through this way to show your age is above 18 without actually leaking it. So this very important property actually when you use zero proof, you can enable identity holder to selectively disclose the claims in a verifiable credential. So this actually allows the developer to build privacy preserving identity systems. This represents also a large category of applications people are exploring. Yeah, of course, in Web3 domain or blockchain domain, many community members like this concept of zero knowledge proof for everything and everyone. So essentially, you can build a zero knowledge version of many applications you have been used today. So in this way, you have the minimum trustless assumption. Also, you don't leak sensitive information when you interact with other services. The application definitely cross like the anonymous payment, identity authentication, also more general purpose verifiable computations. All of those can leverage leverage the powerful zero proof technology to achieve the certain properties. Yeah, basically give you a way to build the trust among different entities and components in your system. Of course, there are also competitive technologies such as the trusted execution environment or confidential computing, if you like to the more industry word. Also, secure multi-party computations. You definitely need to decide it in which situation, which type of technology is most suitable. For example, the confidential computing technology is a more straightforward way to implement to realize the similar goal as zero knowledge proof from the integrity perspective. You can also use the confidential computing technology to basically prove the integrity of data and the program performed in a certain type of hardware. However, this technology rely on the third party hardware manufacturer to protect or to design their system correctly. Zero knowledge proof, on the other hand, they only rely on the cryptography and the mathematics behind this technology. So last, I would like to identify number of research opportunities for this direction. Firstly, let's look at the design space of zero knowledge proofs. From this table, you can see we use basically two categories for the or three categories for zero knowledge proof: snarks, darks, bulletproof. You can see they all have the different trade-offs in terms of the proof size, proof time, verification time. So it's unlikely there is a one scheme can rule them out. So which means you have a larger design space you can explore to make the trade-offs among multiple factors. So this table only show partial of it. So essentially, when you consider to design or choose a zero-knowledge proof systems for your application, there's many factors you need to consider, right? So first one is the security assumptions. Whether your system is based on the discrete logarithm problems over elliptic curves, or rely on the collision-resistant hash functions, etc. Whether you would like to have a trusted setup or transparent setup or updatable setup. Post-quantum security is what you need for your application. Those are all factors you need to consider from the security perspective. What's your performance requirements, right? So the approval time could be linear, could be sublinear in terms of your number of circuit gates, or the verifier time could be constant, logarithm, linear or sublinear, right? So there's all different type of performance profile when you design the zero-knowledge proof systems. What's your bandwidth requirements, right? So how small your proof will be, right? Some proof is very large. Some other proof systems can generate more compact proof. What's your arithmetization techniques? Which type of circuit your system can process or you prefer to process? Also, whether your application require the aggregation type of operations. Yeah, from here you can see basically there's unlimited opportunities for the research in this direction because so many factors you can make trade-off with. So in practice, how actually industry or developer use zero-knowledge proof systems? Actually, there are two ways. The one approach I think is more towards the cryptographer or people has a cryptography background. So this approach is to build a system using a customized system architecture or customized circuit. This approach actually you need to once you know which statement you are going to prove, you are going to build a constraint system basically to represent your statement in a certain form of circuit. Then after using a compiler, you can convert your constraint system into some intermediate representation, and also you can generate a witness. Witness basically means you use your private input and public input to generate the intermediate result. Okay. After if your system require a setup, you will use a public parameter doing the trusted or universal setup. Then you can use a prover after setup you will get a prover key and a verification key, and you will use the prover key and witness to pass to proof systems such as Xinxin and other systems to generate a proof. Then this proof can be verified by a verifier. So this is more complex way for applying the zero-knowledge proof in the industry applications. So this definitely requires the developer to understand the fundamental process, how a particular zero-knowledge proof systems works. So people also explore the other more simpler way is to using the ZKVM. So the idea is that once you build a ZKVM, basically you can prove the virtual machine has processed the transactions. The virtual machine has processed the operation code correctly. So which will make the developer's life much easier. Basically, you can write your statements in a high-level programming language as you using a compiler to convert to a bytecode. This bytecode will be run inside the ZKVM. So ZKVM, after run your bytecode, they will prove every instructions has been performed correctly and generate a proof accordingly. So this proof can be used for any type of application. So this process more target for the general developer community to tap into zero-knowledge proof technology. Yeah, we can see generally speaking, the customized circuit may bring you additional performance advantage because you know how to build that circuit in an efficient way, and how the data will be processed along the way. On the other hand, the ZKVM is a more general purpose virtual machine, which usually take a longer time to generate a proof, because they need to accommodate the different requirements in terms of the proof generation. Also need to accommodate the complexity within this virtual machine. So for a simpler program, you may also take a longer time when you're using the ZKVM. So yeah, actually there's a number of very interesting topics we can continue to explore through the collaboration between industry and universities. First, and also very important topic, definitely is software and hardware acceleration. Yeah, we know the zero-knowledge proofs take a longer time to generate a proof. So if you look at especially those zero-knowledge proof systems using elliptic curves, the bottleneck actually lies in two components. The first one is a variable-based or fixed-based multi-scale multiplication, or MSM. This one definitely is one of the bottleneck. You need to do, instead of a single multiplication, you need to do the multiple multiplication in the size of maybe 2 to 20 to 2 to 25, maybe in this size of scalar multiplication. Also, the other one is a faster Fourier transform or inverse FFTs. You need to do the coefficient conversion to the polynomial or vice versa. So these two components actually occupy a large amount of time during the proof generation for those proof systems based on the elliptic curves. So which also means there's still a lot of opportunities to continue working on the algorithm improvements, also to test it on the different hardware platforms from like the CPU, GPU, FPGA, and ASIC. So this is actually a very important one of the fundamental work need to be further addressed in the next couple of years. For the zero-knowledge proof systems in production mode, we observed most of them rely on GPU to accelerate the proof generation today, which means if you want to use this technology in the smaller devices, like those mini PC, or even on your mobile phone, it just still takes some time to reach to that status. Yeah, second topic definitely is new proof systems. There's a lot of wish list for ideal proof systems, right? So we would like to have proof systems which have the minimal security assumption. Ideally, you don't want to rely on a trusted setup for each program or statement you would like to prove. You would like the proof system has a faster prover and verifier, also smaller proof size. If the proof system can support the proof aggregation, that will become much better. Also, require a low hardware configurations. We know during the proof generation process, you may need to consume a lot of memory or disk storage in your system. Optionally, you may also want your system to be post-quantum safe. If that is a requirement for your future applications. This is definitely a wish list or ideal set of properties for proof systems. It's very hard to achieve all of them through a single design, but the goal is to achieve most of the properties when you design a new proof system. The third topic is more efficient ZKVM or ZKEVM. The ZKVM is more for general purpose computation. ZKEVM is more tied to the blockchain applications. So this is ZKVM. Why it's very important, because you want to more more developers can use this technology. So to design an efficient ZKVM, you may need a more zero-knowledge proof friendly instruction set, which means every instruction can be easily implemented in the zero-knowledge way. Also, you may need to investigate the efficient compiler, also try to support more high-level programming language, like the C, C++, like Golang, also Rust, maybe some others. Yeah, that's a popular high-level program language. Also, we would like to continue improving the prover time using this type of general purpose zero-knowledge virtual machine. Yeah, the last category of topic definitely is more towards the applied research. We know there's tons of research or applications which can leverage the powerfulness of the zero-knowledge proof. Actually, there's many topics has been explored by the startups. Some hot topics, including in the blockchain Web3 domain, for example, the ZK rollups. I have been mentioned before. ZK co-processors. How can you connect the different blockchain systems together through the co-processor? Meaning you can process transactions in the other chain and move from the chain A to chain B in a trust manner by leveraging the zero-knowledge proof. Also, the zero-knowledge proof based on machine learning is also a very important topic. So which will enable you can train the machine learning model in a more trustworthy way. Identity definitely is a very big topic for both Web3 domain, also traditional Web2 domain. For traditional application, definitely for healthcare, financial applications, zero-knowledge proof is also very important technology to, for example, performing the privacy preserving authentication. This includes the logging, the zero-knowledge based logging, or KYC or AML application, etc. Or how can we perform the trustless or verifiable computation, which can benefit for the different industry sectors. Okay, yeah, I think that's all for my talk today. Happy to answer some questions.
Thank you very much, Xinxin. Do we have any questions? There were some comments in the chat. These I think were some links that Yanis was writing.
I will share the slides with you.
Okay.
Out of curiosity, you mentioned there was like another alternative, and I think I probably misheard, but you called it computational computing, I think. What exactly is that?
Yeah, I'm sorry, can you repeat the questions?
You said that there was like an alternative to using like zero-knowledge proofs, where like zero-knowledge proofs rely on like cryptography stuff, but you said it sounded to me like you said computational computing, but I don't think that was what you actually said.
Yeah, so I'm seeing the verifiable computation. That's I think that's one of the large category of applications for zero-knowledge proof. Essentially, one large category applications is you try to prove to the third party you are performing the certain computation in a trustworthy manner. You didn't change the process or you didn't change the input. Yeah, this is the most important properties can be guaranteed by using zero-knowledge proof. Privacy is an additional feature if you need that in your system design.
Okay, thank you.
Any other question?
I have a question. I don't know. Can you hear me?
Yes, yes,
Yes.
Yes. I'm interested in do the zero knowledge proof require a static code? Like like I'm wondering if the proof takes too long, and in the meantime, the code that you are trying to analyze is dynamically changing, especially with AI. Like, is that a scenario that is possible, or is it like too far-fetched to think about?
Yes, that's a very good question, right? So for the different applications, you may require you may have the different requirements, right? So take a blockchain application as an example. You cannot process the proof verification on chain if your proof size is very long, because it's occupied a lot of time or space on chain, and yeah, basically you cannot store that amount of data. The popular ways that people explore is to combine the multiple proof systems, right? So for example, the Stark usually generate they can generate proof faster, but the proof size is long. Let me see whether we have an example give you a feeling. Yeah, for example, this is a simple one, a range proof, saying this private input in these two boundaries, right? So if you do generate a snark proof, you can see it looks very long. This proof cannot be directly processed on chain, right? So the way is that we can compile the Stark proof verification process using the graph 16. So we prove another proof, right? So in this way, we can use graph 16 to comprise the Stark proof. This can be verified on chain. This is just one example. But if you say, okay, all the communication in my system is a server to server communication, you may not care that much for a larger proof size. But if you have the different communication party or processing party with quite diverse computation or processing capability, you do need to think about what's trade-off you would like to make.
Thank you.
Yeah, thank you.
Any other question? Okay. Okay, let's thank the speaker again. Thank you very much, Xinxin.
Thank you.
And okay, so we'll see everybody in two weeks again for the next talk. Thank you very much. Have a good day to everybody.
Thank you. Bye.